Okay, good morning, everybody. Now today we start to talk about new stuff, right? The fuel utilization. And we have two different parts, and one is focusing on the regulation of fuel utilization response to food intake, and the second part will be fuel utilization during exercise, right? So we actually have three different physiological conditions in the metabolism that we need to learn. Two nutritional status, right? Fat state versus fasting state, and the third physiological condition is exercise, right? So what we're going to focus in this part is that we're going to learn the differences among the tissues in utilization of fuel during feeding and fasting or starvation. We know that different tissues, they do a different metabolism, right? In both glucose and fatty acids, so far we learned, but of course protein metabolism can also be different, but we haven't learned yet. And also we wanted to know the branching point in metabolism. So, we learned lots of very complicated metabolic pathways, right? And in both glucose and lipids, fatty acids metabolism, but this metabolic pathway are connected. So we want to learn several key points, or in other words, in the key metabolites that connected all the different metabolic pathways, right? And also tissue-specific fuel metabolism. For example, glucose can be metabolism differently in liver versus muscle or brain, like or red blood cells. And lastly, we wanted to know, the adipose tissue in fuel metabolism. This is something, I kind of like it because my lab is working on the, research in the adipose tissue. We kind of interested in adipose tissue. So adipose tissue, we know traditionally, right, we view adipose tissue as the storage organ, basically store lipids, right? But recently, well, not recently, but at least decades, right, people realize that adipose tissue not just passively store energy, but actively involved in the metabolism by secreting or releasing the very important hormones or peptides and other metabolites, right, and regulate whole body metabolism. So we're going to talk about the adipose tissue function in the regulation of metabolism. So let's talk about metabolic fuels. So what is a metabolic fuel? There is a definition for this. So metabolic fuel is the metabolic compound that present in the circulation, and it also can be taken up by tissues for energy production. So two concepts that you need to remember in terms of metabolic fuel. First is the metabolic compounds have to be present in the circulation, right? And second, this metabolic compound can be used for ATP production, right? Not everything present in the circulation are the metabolic fuels, right? Only the compound that can be oxidized and used for energy, for ATP production. So, so what are the major energy fuels that we have already learned? Have you guys named a few? Let me see how many. 1, 2, 3, 4, 5. 5 bullet points. That means we have learned 5 metabolic fuels that can be used for energy ATP production. What else? Carbohydrate, glucose, right? And fatty acids, right? Yes. Ketone bodies. And we have two more, right? Yeah, amino acids. One more. Let's see. Glucose, right? Fatty acids. Triglyceride, right? Well, actually fell into the same category, right? Fatty acids. So, ketone bodies and amino acids, right? So these are five major metabolic fuels that our body can use for energy production. And one very important point that I want to make is that not all metabolic fuels are available at the same time. What does that mean? Say that again. Yes, based on the physiological condition, whether it's under the fat or fasting condition, right? For example, ketone bodies will not be present at a high concentration under fat condition, right? Only under the fasting, particularly prolonged fasting condition, then our body produces a lot of ketone bodies and raise the ketone bodies levels in circulation, and then can be used for energy fuel. So keep in mind, depend on the physiological condition, right? We probably wanted to know what type of energy fuels are available under fat condition versus fasting condition, right? And metabolic fuels can also be divided into the two main categories, the endogenous or exogenous. Endogenous, exogenous, right? Exogenous. Sorry, I think I exogenous, right? So that means one type of energy fuel that's present in the circulation that our body can use for ATP production are from diet, right? Which mainly, used under the fat condition. And the other type of category of energy fuels that our body can make. So, for example, actually not yet. So, first of all, the two main categories, right? Exogenous and endogenous, from diet or our body make. And endogenous, in terms of endogenous fuel, we can further categorize or divide it into, the different types. One is stored fuels. We have 3 bright points for stored fuels, energy fuels. What are these? Stored energy fuels. Glycogen, fatty acids, I heard somebody, right? Or triglyceride. And you mean, yes, amino proteins, right? Although we have not talked about protein yet. 3 main stored energies or energy fuels are triglyceride, glycogen, and protein, right? And what about the fuel made by our body? Fuels made by our bodies? 2 type of fuels. Yeah, ketone bodies One more. Glucose, right? Glucose. We can make glucose from non-sugar precursors, right, through gluconeogenesis, and the ketone bodies are made from acetyl-CoA, right? So during the fat condition, when we have enough energy fuel that we can obtain from the diet, right? So the major fuel that can be utilized by all the tissues under fat condition is glucose, right? So glucose is the main energy fuels that can be utilized by all the tissues under the fat condition. And this glucose basically is from diet, right? And under the fasting condition, when we don't have enough, energy fuels from the diet, so our body can adapt in order to keep the blood glucose level within the normal range, right? And also we need to provide energy to tissue for basic functions, right? The activities of tissues, and also for survival. So that means we need to either to break down stored energy, glycogen or triglyceride, right, to provide energy for other tissue use. We also make the energy fuels like glucose and ketone bodies, right, for energy. So this kind of information, I think we talked about before, but just try to, put all them together and, in a comprehensive way so we can understand metabolism better. Now, the fat and fasting condition, our body utilizes different sources of energy. We also can make energy, right? The energy fuels. And here we just divided, the two different states, and to further understand how our body stored energy during the fat condition, right? So we kind of balance, under the fat condition, because we are able to get the energy fuels from the diet, so we don't need to utilize stored energy, and we don't need to make energy. But instead we actually stored energy from the diet if we don't use them all, right? So and fasting will just go the opposite way, but we need to break down the stored energy and make energy fuels. So under the fat condition, our body stored excessive energy in two forms, right? Everybody knows, right? We already talked about it. The first is glycogen, right? We convert an excessive carbohydrate from the diet to the glycogen and stored in which tissues? Liver, muscle, right? So liver and muscle are the two main tissues that store glycogen. And the second form of the stored energy is triglyceride. And again, adipose tissue, right? It's a main tissue for storage triglyceride. But I also want to mention that in addition to adipose tissue, muscle and liver can also store some of the triglyceride, but the amount is very small, right, compared to adipose tissue. And under the fasting condition, we utilize stored energy, and we also make energy. So the main, actually 4 different pathways that need to be active during the fasting condition to provide energy. First, the glycogen breakdown pathway need to be active, right? We need to break down glycogen. And secondly, we make glucose through the gluconeogenesis, right, to maintain blood glucose level and also to provide energy for other tissues. And triglyceride also need to be break down to release fatty acids. And lastly, we make ketone bodies. And amino acids can also be used for energy fuel only when we fast for a long time, all right? So I put this order, glycogen breakdown and gluconeogenesis, fatty acids release, and ketone body synthesis, and amino acids utilization in kind of this order. And I think our body actually does, the adaptation or whatever called in this order. That means when the starvation, for early stage of starvation, then our body first of all break down glycogen, right, to utilize the glucose, and then secondly we start making glucose. And when starvation goes longer, then we break down the triglyceride and utilize fatty acids, and prolonged, longer than 2 days starvation, then we start to make ketone bodies, right, and also break down the proteins to utilize amino acids for energy. So we have kind of priorities, right, which energy fuels would be used first, and then the others. So under the fasting condition, our body tried to do something to spare glucose and amino acids. So keep this in mind, so we can understand when we break down or when we oxidize glucose during fasting condition. In most of the tissues, we only goes partial oxidation, only goes the glycolytic pathway, right, and produce lactate. We don't want to break down lactate further for complete oxidation, because we try to spare skeleton, carbon skeleton for the use of the lactate for gluconeogenesis, right, so for making glucose again, recycle the lactate. Once the lactate is break down to acetyl-CoA, then acetyl-CoA cannot be able to use for gluconeogenesis anymore, right? So that is, the reason that we only partial oxidation glucose, not for complete oxidation glucose. Okay, now let's talk about something about the transition among the different metabolic fuels. We already know that some of the nutrient or energy fuels can be converted, right, each other, but not all of them. So let's see. So how about a protein? What do you think that can protein be converted to carbohydrate? Yes? You nod head. Through which pathway? Protein amino acids converted to glucose. Which pathway does this? Gluconeogenesis, yes. Right. Oh, sorry, I wrong way, but anyway. So carbohydrate we know can also be converted to fat, right? And which pathway does this? lipogenesis, right? Lipogenesis. So lipogenesis can convert glucose or carbohydrate to fatty acids, right? Fat. And let me see which one. Okay, so protein, then you already mentioned that, yes, protein or amino acids can be converted to glucose, carbohydrates through gluconeogenic pathway, right? And what about a protein conversion to fat? Can our body do this? Can protein be converted to fat? Yes, right? How? Okay. Yeah, I know we have not start to talk about protein metabolism yet, right? So protein can be oxidized to acetyl-CoA, right? The three nutrients, glucose and amino acids, fatty acids, can all be oxidized, break down to acetyl-CoA. So acetyl-CoA is really important, right? Connect all the three nutrient metabolism. So acetyl-CoA is the starting molecules, right? Fatty acid synthesis, right? So now we have all kind of connection, right? Among these three macronutrients or metabolic fuels. Now, how about the opposite direction? We know that can carbohydrate be converted to protein? Are there any pathway exist to convert carbohydrate to proteins? No, right? No. And how about fat to protein? No, right? No. How about a fat to carbohydrate? Fatty acids or lipids can be converted to carbohydrate. Can we use lipids to make glucose? No. But actually, we have an exception. If you still remember, glycerol considers, the type of lipids, right? And propionyl-CoA, I mentioned before, I guess, probably one time or a couple of times, as also can be used for gluconeogenesis, right? So glycerol and propionyl-CoA are the precursors of a gluconeogenesis, you still remember, right? So this two type of lipids is kind of exception, right? So now let's see how specific type of lipids can be converted to glucose. Let's talk about the glycerol first, right? So this is a pathway that tell us how glycerol being used for gluconeogenesis. Glycerol kinase is an enzyme that present in the liver, right? It can phosphorylate glycerol to glycerol 3-phosphate. Remember, right? And glycerol 3-phosphate can be converted glycerol aldehyde 3-phosphate by this enzyme called glycerol 3-phosphate dehydrogenase, right? And this is the intermediates, if you still remember, in the glycolysis pathway, right? And this can be used for gluconeogenesis. But you don't have to remember the pathway like reaction in this process, but just remember, you know that glycerol can be used for gluconeogenesis, right? And propionyl-CoA is another type of a specific fat that can be converted to glucose. The propionyl-CoA is generated from oxidation of all-chain fatty acids and the branched-chain amino acids, right? The two sources of the propionyl-CoA production. One is the oxidation of all-chain fatty acids I explained earlier, right? The even-chain fatty acids is oxidized through beta oxidation, finally generate the acetyl-CoA, right? The two carbon molecules. And all-chain fatty acids oxidized and generated acetyl-CoA and plus the propionyl-CoA. Propionyl-CoA is a 3 carbon molecules, right? And branched-chain amino acids can also be oxidized to produce propionyl-CoA. We're going to talk about later in protein metabolism session. So this is a pathway how propionyl-CoA can be used for gluconeogenesis. One first step is the propionyl-CoA carboxylase. So carboxylate propionyl-CoA to methylmalonyl-CoA. And the next step is methylmalonyl-CoA is converted to acetyl-CoA, right? By this enzyme, methylmalonyl-CoA mutase. And acetyl-CoA is one of the intermediates in the TCA cycles, right? So acetyl-CoA joins TCA cycles and goes through part of the gluconeogenic pathway, converts to oxaloacetate and PEP and gluconeogenesis, right? So again, you just need to understand this process, how propionyl-CoA being connect to the gluconeogenic pathway, right? The acetyl-CoA is a key, right, point. All right. So what are the substrates that can lead to different metabolic pathway in metabolism? That here we're going to talk about the branch points in metabolism. Right. So the key points, that means the key metabolic point that can connect the multiple metabolic pathways, right? So we going to talk about the 4 main key points in the metabolic pathways: glucose 6-phosphate, pyruvate, acetyl-CoA, and succinyl-CoA, right? And I guess you guys are familiar with, right, this metabolites. So let's talk about the glucose 6-phosphate first, and this is very important key points. Metabolite and connects many metabolic pathways, particularly in the glucose metabolism, right? So pathways that can generate glucose 6-phosphate, the 3 metabolic pathways can generate glucose 6-phosphate. First is glycolysis, right? The metabolized glucose metabolized to glucose 6-phosphate. Second is glycogen breakdown pathway, right? So glycogen can be break down and to glucose 6-phosphate, and then glucose 1-phosphate, and glucose 6-phosphate, and eventually to free glucose, right, by glucose 6-phosphatase. And last is the gluconeogenesis pathway, right? So glycolysis, gluconeogenesis, and glycogen breakdown, and these three pathways of glucose can generate glucose 6-phosphate. And next, the pathway that can use glucose 6-phosphate, glycogen synthesis pathway, right? So, so glucose 6-phosphate can be isomerized to glucose 1-phosphate, and then the following the glycogen synthesis pathway, and glycolysis and pentophosphate pathways, right? Glucose 6-phosphate is the first substrate of the pentose phosphate pathway, right? Any questions so far? Now, second key point in metabolism is pyruvate. So this is a diagram show you the position of the pyruvate in the metabolic pathway, multiple metabolic pathways, right? Pyruvate can be generated from oxidation of glucose and a number of amino acids, right? And also lactate. But the pyruvate can be used for further oxidation to acetyl-CoA and finally enter the PTC cycle. And also acetyl-CoA can be used for synthesis of fatty acids, ketone bodies, and cholesterol. And pyruvate, also is one of the gluconeogenic precursors, right? So pyruvate can be directly converted to oxaloacetate to enter the gluconeogenic pathway, right? So pyruvate is again very important metabolite that connect the glucose metabolism, amino acids metabolism, right, and also lipids metabolism. And acetyl-CoA is another important key point, metabolic point. And first of all, the three macronutrients, fatty acids, glucose, and amino acids can all be oxidized to generate acetyl-CoA, right? And acetyl-CoA is also served as the substrate for the synthesis of multiple metabolic compounds, right? Such as fatty acids, ketone bodies, and cholesterol. Of course, acetyl-CoA can be further oxidized through TCA cycles for energy. So I would just use the same diagram that we used for the pyruvate for acetyl-CoA, right? So acetyl-CoA is just downstream of the pyruvate, and it can be entered completely oxidized TCA cycle or be used for synthesis of a three lipids compound, right? Fatty acids, ketone bodies again, cholesterol. Okay, succinyl-CoA is also very important, the key metabolites, and it is generated from oxidation of branched-chain amino acids and alt-chain fatty acids, right? So succinyl-CoA connected branched-chain amino acids, alt-chain fatty acid metabolism, right? And So the succinyl-CoA it's actually the part of the TCA cycle, right? And can be used for gluconeogenesis. All right. So this again is a very important key point that connect branching amino acids, all-chain fatty acids to gluconeogenesis, right? To glucose production. So this slide, I put all these four key metabolic points together, and so you can see kind of probably kind of complicated, but I hope it is comprehensive, to help you understand all these different metabolic pathways connected by particularly, these four key points, metabolic key point, right? The glucose 6-phosphate, pyruvate, acetyl-CoA, and succinyl-CoA, right? So glucose 6-phosphate basically connected multiple glucose metabolic pathway, right? Glucose, the glycogen synthesis and gluconeogenesis, right? And the PPT phosphol. The pentophosphate pathway, right? And pyruvate connected protein metabolism pathway, lipid and glucose metabolism pathway, right? Pyruvate can be generated from amino acids, glucose metabolism, and lactate, and it also be used for gluconeogenesis and lipid metabolism, right? So, the succinyl-CoA again connected the branching amino acids and all-chain fatty acid metabolism to gluconeogenesis pathway, right? So, I'm not going to go to detail, but I just hope that this slide will help you to, comprehensively understand the connection, between different metabolic pathways. Okay, any questions? All right. Now let's talk about the specific metabolism of fuel in different tissues, right? Different tissues have a different metabolic function, metabolize nutrients differently. Let's talk about brain first. So brain, we know the only certain type of fuel can be used, right, for ATP production. Glucose definitely is the primary energy fuel that brain can use. And brain can also use the ketone bodies. Sometimes can utilize lactate. And brain lacks a stores of energy, right? Brain is not able to store any type of energy fuels, right? Brain doesn't store glycogen, doesn't store fatty acids. So they heavily rely on the glucose for energy. So for example, in the fat state, the glucose need the 60% of the actually glucose utilized in the body by brain. So brain actually utilize 60% of the glucose, right, in the body, in the fat condition. And brain can release some metabolic compounds or fuels, for example, lactate, but only in the very long time starvation, right? And during the prolonged starvation, the ketone bodies are become important, right, for brain, because we have a limited glucose, available. So ketone bodies can be oxidized by brain. And I think we explained before, right? Brain cannot utilize fatty acids for energy because of the uptake issue. So ketone bodies made and primarily used by the brain. And secondly, under the prolonged fasting condition, glucose is only oxidized partially. Normally, under the fat condition, right, the glucose completely oxidized in the brain, but under the certain condition, a very long-term starvation, brain also try to spare the carbon skeleton, right? So, and also partially oxidize glucose through the through the glycolysis pathway, and so lactate will be released by the brain. But again, it is, only under the very, very long-term starvation. So what is the preferred fuel that brain use? Again, of course, glucose, right, is the first choice, and then ketone bodies under the prolonged starvation, and lactate only in some pathological conditions, for example, hyperglycemia condition, right? We have a very, very low blood glucose level under this condition. Then, because of other tissues utilize glucose partially and produce a lot of lactate from other tissues, so that makes the blood lactate levels increase a lot. So then, under these conditions, then you have some, the lactate available. So brain can utilize lactate for energy only under the pathologic condition, hyperglycemia, right, conditions. And also in the prenatal stage, brain can also utilize lactate just for the development of the brain or kind of purpose, right? All right. So again, a preferred fuel for brain is glucose, and under the prolonged fasting conditions, the ketone bodies can be used, and under pathologic conditions like hyperglycemic state, that brain can also use some of the lactate for energy, right? Let me just stop here and we'll take a break. Okay, so we finished this slide. Now, let's talk about skeletal muscle for full utilization of metabolism. So full utilized in skeletal muscle or by skeletal muscle are, you guys know, right? Glucose, fatty acids, ketone bodies, and amino acids, right? So all type of energy fuels can be used by muscle. So muscle is very easy to handle, right? They, can use any type of energy fuels. So again, depend on the physiological condition. Fat condition, muscle primarily use glucose, and fasting condition primarily use fatty acids, right? Ketone bodies and amino acids. So what is the preferred fuel in the fat state? or under the bus of the activity like exercise. So, let me see. Glucose, yes, glucose. And what is a major fuel in resting muscle in the fasting condition? Fasting state. What if? Fatty acids, yes. So fatty acids is a major fuel used by muscle during the fasting condition, because we're not talking about exercise, right? It's a resting condition. Yes.
How about exercise in the fasting state?
Yeah, the glucose. Glucose still is the primary energy fuel that muscle use, right? In the fat condition and or during exercise. But we have a specific session talk about exercise. A little bit different, depending on what type of exercise, right? So during the fasting condition, fatty acids are able to meet 80% of energy, right? For muscle. And muscle is able to release some of the energy compounds like lactate, alanine, and glutamine, right? Usually released from muscle. If you still remember, we talk about 2 cycles, right, in the gluconeogenesis. So muscle is a major contributor, right? That involved actively in these 2 gluconeogenic pathways cycles, which are chlorine cycles and alanine cycles, right? Chlorine cycles, muscle contribute lactate for making glucose in the liver, and alanine cycles, muscle release alanine and be used for gluconeogenesis in the liver, right? And muscle is also able to store energy. What type of store energy? That muscle. Glycogen, right? And triglyceride. So triglyceride again, primarily stored in the adipose tissue, but muscle can also store some triglyceride. It's very important for energy use during exercise, right? So in the vigorously contraction muscle, the partial glucose oxidation will produce lactate, right? So glucose is not always completely oxidized in the muscle during exercise. Depend on what type of muscle type, fibers, and what type of exercise, right? Again, we're going to talk about later. So glucose can be complete oxidation or partial oxidized to produce lactate. And protein can also be break down to produce alanine for the energy, again, during the exercise, right, muscle contraction. Any questions? Okay. So glycogen stored and used locally, you guys all know, right? Because of which enzyme that lacks that glycogen will not break down to release glucose. Which enzyme that is lacking in the muscle that makes muscle only use glucose locally. Yeah, glucose 6-phosphatase, right? So glycogen being breakdown but utilized within the muscle. Muscle is not going to release glucose because of lacking glucose 6-phosphatase. But muscle is able to contribute to circulating glucose indirectly, right? In particularly two ways. First is through the gluconeogenic cycles, right? Chlorine cycles and alanine cycles. So muscle release lactate and release alanine for making glucose in the liver. So indirectly contribute to circulating glucose. And the other way is the protein degradation, right? You release the amino acids from the muscle and for gluconeogenesis. And not just the alanine, but the other gluconeogenic amino acids, for example, glutamine and glutamate, right, are also gluconeogenic as the precursors. So glutamate also released from muscle and being converted to alpha-ketoglutarate and succinyl-CoA, and then the oxaloacetate, gluconeogenesis, right? The pathway, remember. So again, muscle can contribute to circulating glucose through the two different ways. First is through the chlorine cycles and alanine cycles, and second, through the release the glutamate for gluconeogenesis, right? But if you're thinking actually the pathway, actually the two pathways, right? One is the the lactate, release lactate for gluconeogenesis, and second is release amino acids including alanine, glutamine, glutamate for gluconeogenesis, right? So in the fat state, again, glucose is the main energy fuse for muscle, for ATP production. And in the fasting condition, resting, right, fatty acids and as the main energy fuse. And under the strenuous activities, the glucose again is the important energy fuse. But under the prolonged starvation, fatty acids then become more important energy fuse, right? So and ketone bodies were also important energy fuse. And under again the prolonged starvations, glucose and amino acids will still be used, but as not as a primary energy fuse for muscle, right? Again, prolonged starvation, fatty acids and ketone bodies become the primary energy fuse for skeletal muscle, and muscle will also continue to use glucose, but only goes partial oxidation, and muscle can also use some of the amino acids for energy. So keep in mind our body also always try to spare glucose and amino acids, right, for use as energy. Kidneys. So kidney basically is able to utilize all type of metabolic fuels, including glucose, fatty acids, ketone bodies, lactate, and glutamine amino acids. And kidney usually complete oxidize this energy fuse, right? So for glucose, kidney can do the gluconeogenesis and TCA cycles for complete oxidation. And fatty acids goes to beta oxidation, and ketone bodies can also be oxidized through TCA cycles, right? And lactate, alanine. All energy fuels can be complete oxidized in the kidney for ATP production. And kidney not only utilize all the type of energy fuels, but it also very important contributors, right, for energy production. So kidney, we know that is second important organs, right, for gluconeogenesis. So kidney basically can utilize a variety of amino acids for gluconeogenesis, and kidney is also able to release glucose into circulation because it has a glucose 6-phosphatase, right? Kidney. Okay, intestine tract. So small intestine, I think we mentioned earlier, the amino acids basically is the primary energy fuel, right, for small intestine. For example, glutamate, and are the most important energy fuels for small intestine. And I think I count about the 80% of energy, right, in small intestine from amino acids oxidation, and about 20% of energy from glucose oxidation. So under the fat condition. So under the fasting condition, small intestine can also utilize fatty acids, ketone bodies, right, for energy. And glucose basically is partially oxidized in the small intestine and produce lactate, right, and lactate can also release into the circulation. And the glutamine is also actually partially oxidized, right, for generating lactate, pyruvate, and alanine. So colon is kind of unique and specific. So in terms of energy utilization, so colon usually utilize the butyrate. It's a short chain fatty acids, right? Butyrate as the energy. So short chain fatty acids is produced in the colon by the fermentation of dietary fibers, right? If you guys know, so colon utilizes lots of butyrate, short chain fatty acids for energy. Okay, red blood cells, relatively simple, right? Because of which organelle is not present in the red blood cells. Mitochondria, right? Because red blood cells lacks mitochondria, so makes them only use glucose for energy, and also glucose only goes partial oxidation, right, for lactate production and some ATP production. So, and here I just mentioned which pathway that red blood cell is able to perform. The pentophosphate pathway, right? Because it is very important. The 5-carbon sugar phosphate that be used for to maintain the integrity of red blood cell membrane, right? So this pathway, pentophosphate pathway, is very active in the red blood cells. Okay, liver. So in the fat condition and liver, 20% of blood glucose is taken up by the liver. So liver can do several important metabolic pathway, right? Glycogen synthesis and fatty acid synthesis, pentophosphate pathway, and also okay, so in the fat condition, 20% of blood glucose is taken up by the liver for synthesis of glycogen, right? And also for conversion from glucose to fatty acids, lipogenesis, right? And pentophosphate pathway is also active in the liver, and liver is able to store glycogen and also some of the fatty acids in the form of triglyceride, I mentioned, similar to muscle. So liver can also store some amount of triglyceride, but not much, right? If we have too much triglycerides stored in the liver, that become fatty liver disease, right? But under normal condition, liver still, contains some amount of triglyceride. And in the fasted condition, and liver is the main source of endogenous energy fuels, right? You all know. Glycogen break down gluconeogenesis, right? Which the last pathway will contribute to store energy or making energy, endogenous energy. Ketogenesis, right? So glycogen break down to release fatty acids, gluconeogenesis to making glucose, and ketogenesis, right, making ketone bodies. So liver is really, really important organ that, in terms of the energy metabolism, can store energy and make energy, right? And utilization of fuels in the liver, a little bit different from the other tissues. So liver utilizes amino acids, glucose, and fatty acids, right? And, three type of energy fuels that liver can use. But liver cannot use which energy fuel that liver cannot use? Ketone bodies, right? Ketone bodies. The liver cannot utilize ketone bodies because of liver lacks succinyl-CoA transferase, right? Okay, that's good. And another important thing is that liver's preferred fuels is not glucose and not fatty acids, but it's alpha keto acids, right? So alpha keto acids is the preferred fuel that liver use, which is metabolized from amino acids, right? So amino acids metabolize and produce a lot of alpha keto acid, which can be used by the liver. So liver, again, preferred fuel, energy fuel is alpha keto acid from amino acids metabolism, right? And liver usually converts most of the carbon skeleton as a glucose, right, and store in the glycogen. What this I think we talked about already. And fatty acids limited, oxidation limited for ketogenesis, right? We also talk about this. Under the fasting condition, liver picks up fatty acids and oxidize through the beta oxidation to generate acetyl-CoA. Acetyl-CoA will not be complete oxidized in the liver, rather it is used for ketogenesis, right? And glucose also partial oxidize to lactate, and again the purpose is to save the carbon skeleton, right, for gluconeogenesis. So again, liver prefer to utilize alpha keto acid for energy and oxidize all the nutrients through the partial oxidation pathway, right? For fatty acids, partial oxidize to acetyl-CoA and for ketogenesis, and glucose partial oxidized to lactate, right? So since this is a release of several fuels, right? We know that liver can release glucose, right? So which two metabolic pathways that contribute to the release of glucose from the liver? Two pathways. Glycogen breakdown, right? Glycogenesis and gluconeogenesis, right? So these are the two metabolic pathways that contribute to the release of glucose from liver. And liver, of course, can also release ketone bodies, right? And triglyceride. But the release of glucose, ketone bodies, and triglyceride is it's actually different under the different physiological condition. So, for example, under fat condition, liver basically release triglyceride, right? Not a glucose and ketone bodies. And under the fasting condition, liver primarily release ketone bodies and glucose, right? But not much triglyceride. Does that make sense? Right? So fat condition, because liver picks up a lot of fatty acids from the diet and convert it to triglyceride. Because the triglyceride need to go to the final destination to adipose tissue, right? So lots of triglyceride synthesized from the dietary fatty acids and packed into VLDL and released into circulation, transport triglyceride to adipose tissue. So under the fat condition, the triglyceride are released through the VLDL, right? And fasting condition, you guys probably all understand, right? The glucose, breakdown from glycogen or gluconeogenic pathway and need to be released in circulation, and ketone body as well. Okay. So I think I prepared 2 slides and tried to separate the fat and fasting condition to help you understand the metabolic flow, right? Which metabolic fuels are synthesized and which metabolic fuels are released into the circulation, right, from the liver. And again, depend on the fat fasting condition, and that will involve the multiple metabolic pathways. So let's look at the fat condition first. So we eat a meal, right? So we get carbohydrate, lipids, fatty acids, and amino acids from the diet. So liver need to deal with all this. So first, the carbohydrates, glucose, basically in the fat condition, uptake glucose, by liver uptake glucose from the circulation and for the synthesis of glycogen, right? And glucose from the diet can also be oxidized through the glycolysis pathway, and to produce pyruvate. And pyruvate under the fat condition in the liver can be further oxidized to generate acetyl-CoA, right? And acetyl-CoA, some of the acetyl-CoA goes to the TCA cycle for complete oxidation. But most of the acetyl-CoA will be used for fatty acid synthesis, right, under fat condition in the liver. And these fatty acids being converted triglyceride and packed into VLDL and secreted into the circulation, right, under the fat condition. So this is one pathway. And of course, we also liver picks up a lot of fatty acids from diet in the Carmichael remnant, and this will also contribute to fatty acid pool in the liver and be converted also back to triglyceride and released in the VLDL, right? And then the amino acids, we also get a lot of amino acids from the diet, and depending on what type of amino acids, so some type of amino acids, for example, alanine, serine, and glycine, and threonine, cysteine, and tyrosine, all these amino acids can be metabolized to pyruvate, right? So pyruvate then goes through the different pathways. One pathway that can be oxidized acetyl-CoA and converted to fatty acids through the lipogenesis pathway, right? And for triglyceride synthesis. So this is the pathway for how amino acids can be converted to fat, right? So amino acids being metabolized to pyruvate, acetyl-CoA, and lipogenesis, fatty acid synthesis. And pyruvate that generated from amino acids can also be metabolized to glucose 6-phosphate, and this pathways, glucose 6-phosphate, can be used for glycogen synthesis, right? So amino acids, particularly this 6 type of amino acids, can be used for fatty acid synthesis and also being converted to glycogen, right? And pyruvate converts to glucose 6-phosphate through the gluconeogenic pathway, right? So I wanted to mention to you that the gluconeogenesis, of course, is very active in the liver under the fasting condition, right? But it's also active in the fat condition. But the purpose is different. For example, here, pyruvate through the converts glucose 6-phosphate through gluconeogenesis pathways, but this glucose 6-phosphate is not going to convert in free glucose, but to the glycogen, right? So again, but just body use similar gluconeogenic pathway for glycogen synthesis and not for glucose release. Right? That makes sense. Depend on the reason, because of the glucose 6-phosphatase, the activity is low under the fat condition. So glucose 6-phosphate cannot be converted to free glucose and released under the fat condition. Right? So only under the fasting condition, when liver, we have a very high